So my name's Torsney Weir. Right now I'm a postdoc at the University of Vienna. And I'm going to talk about, so the title of my talk is Slicing Multidimensional Spaces. And there's actually like a lot of application areas which I'm going to touch on. So hopefully it won't be quite as abstract as the title may seem. So in terms of about me, so actually this is the boring version. So I have pictures. So I was born in Allentown, Pennsylvania, which is why my accent is so amazing. If you don't know where Allentown is, it's there. It's boring. I lived there for like a year, and then I moved around a lot, and I don't remember much of that. But then I finally went to undergrad. I went to Georgetown University, which is in Washington, D.C., and that's the campus. It looks very like classic campus. And then I worked in New York City for like 6 years, working in finance, like building risk management systems, front office risk management systems. That was fun, but then it got boring. And I missed mountains, and I missed nature. So I moved to Vancouver, which looks like that. That's a real picture of Vancouver. So I moved there actually to go skiing and scuba diving. And I didn't know anyone, so I started a master's in visualization. And it turns out I liked it a lot. So I did a master's in visualization, and then my supervisor was like, oh, I got a job in Austria. If you want to do a PhD with me, you have to move here. And I said, oh, that's interesting. So then I moved to Vienna, which is where we are now. That's where we are, if you're not sure. And I finished my PhD last year, and now I'm doing a postdoc there. And the story continues, actually. Next is I'm moving to Swansea University, which looks like this. Kind of looks like a flat version of Vancouver, I think. There are hills, but behind it. If you don't know where Swansea is, it's here. This is also Wales, which I also learned recently where that is in terms of the United Kingdom. So that's me. So I'm moving there in June, actually, which is exciting for a lecturer position. Okay, anyway, but I'm here mostly to talk about my research, and my research has sort of been kind of doing a bunch of things around looking at what are called multidimensional spaces, but also looking at sort of the users of these people who want to look at multidimensional spaces and the tasks they want to do. And then also I also am into I love programming and programming languages, so I'm started doing a lot more work now on API design, and getting my work out also is helpful as libraries that people can use. So the general problem with multidimensional spaces is the 4D cube isn't animated anymore. That sucks. Okay, anyway, but if you're looking at squares, like we have ways of looking at squares. So there's like 2D, everyone knows what a square is. In 3D, it's a cube. In 4D, you can actually do animation. This is like that animated cube where the thing goes inside it all the time. But as you go into higher and higher dimensional spaces, like we don't have actually ways of looking at these things. So this is, and it turns out these things are actually very useful in a variety of contexts. And so that's where I came in, and I was basically working on sort of basically looking at slices of these multidimensional spaces. So the idea here is that it gives you sort of a general overview of what's going on in the space. And it's a relatively easy to understand metaphor. So I think most people, like, they understand, if you like cut an apple in half and you look at the inside, that's how you can look on the inside. So this is the same thing just for like, just generic objects. So I mean, here, this is an example. So this is actually from like sort of the first paper that worked on this, called Hyperslice. But here, this is the 3D representation of the shape, and then these are all axis-aligned slices of the shape through the center. And that's why you can see sort of here's the gray part, this is the gray part here, and you can see the panels when you take the slices. And you can extend this to all kinds of other objects into any sort of arbitrary amount of space. And the nice thing is, by sort of looking at these cross-sections, you can get a sense for what these objects look like so you can get a sense for these multidimensional spaces by looking at 2D sort of slices of these objects. So I mean, if you go back to our cube example, this is what sort of the multiple slices of a cube looks like. It's not very exciting. They all look like squares because you're basically slicing a whole bunch of squares at a time. And each one of these plots, this shows the pairs of dimensions. So this is like the x2 and x1 dimension, and this is the x1, x3. So that's why you get 3 plots. But now you can actually look at more complicated things. So now you can like look at hypercubes, and you can see that the cross sections are also all squares. You see these cross lines. These are due to the meshing algorithm that I used to basically fit a mesh over a bunch of points. So you're actually seeing those crosses when you look at it. But you can this method sort of extends to any number of dimensions in terms of space, and so that's the nice part about it. And the question really is, how do you generate these things efficiently, and what are good ways to sort of let the user browse through them. And so everyone kind of knows what a cube looks like. Another thing that's quite popular is a thing called so it's fun in geometry. There's all kinds of like crazy names for things. So this is an 8-sided figure, like an 8-sided die. If you play like Dungeons and Dragons or whatever, its technical name is an orthoplex. But the 3D version looks like this. There's a 4D, so there's a thing called a Schlegel diagram, which is used for looking at 4D objects. And the 4D version of, the 4D version of this as a Schlegel diagram looks like this. It's basically projecting everything inside one of the faces. But I don't think it really tells you much about like the actual characteristics of the shape itself. And the idea is that actually if you look at the cross sections, you actually get a sense that this has like symmetry in all these different dimensions, and kind of relative size for how things change as you take different slices. And so what you're looking at here for every one of these, you basically take a whole bunch of slices of this 4D object, and you project them all down, and you look at them in here. And then like we have sort of, I like to think they're creative ways of sort of browsing through these slices to kind of get a sense for what's going on. And if you extend this to 5D, you can again see that this sort of structure is always repeating, and so this thing always has these symmetries in any number of dimensions, and this is really nice. So it's very abstract still. I know. I'm sorry. So I'm going to stick with a concrete example of something that actually people do all the time, and we use machine learning. One thing you might have is like, you want to buy a house in Boston or something. Just for an example, it's actually because I have a data set. There's a Boston housing data set. So you want to buy a house in Boston, and you have a bunch of questions about what kind of house you want. So you have like, what's the most expensive house? That's pretty easy. You can look it up. But you might want to know like what sort of factors contribute to the house price, and you want to know how does the house price change with certain types of factors, so like safety of the neighborhood. And you might care if like the relationship between them is sort of linear or logarithmic or something like that. So maybe it basically changes smoothly over time, or maybe it goes up really quickly or down really quickly. This you might want to know if you're going to buy a house and invest in an area. And the problem is you can do sort of the first one by taking like a whole bunch of discrete houses and looking at the data. But if you want to answer these other questions, what you need is sort of a more continuous model. So you want sort of basically it's a regression problem where you want to put in, all the different prices, all the different factors of the house, and then it tells you what the price of the house should be. Of course, if you could really make one of these, then you could make tons of money. But so I don't know anyone who's made one of these. We tried to make one of these when I worked in finance because I worked in mortgage-backed securities, and it didn't work. So the company went under. But yeah. So these are kinds of things that you would want to know. And like the standard approach to sort of building a continuous model. So you have a whole bunch of houses, and now you want to build a continuous model, and this is a regression problem. And so, the standard way, we have this nice thing called the UCI housing data set. It has 13 different things about the house, and it has this thing which is the home price for an area. And these are sort of the key factors, so that they're all abbreviated in the data set with these really uncreative names. And this is what they mean, and I'm going to refer to these four in the rest of the presentation. But in terms of building a machine learning model, you basically can take your data set. So here are all the 13 factors of your house. Here is your home price. You feed this into your magical robot machine learning algorithm that tunes itself. You get this magic function. And then the question is how do you look at it? And sort of the standard approach is to basically use as many dimensions as possible, and sort of plot something like this, which has a lot of colors, and it's hard to figure out what's going on, and there's actually like occlusion problems from like what's behind this peak, you don't know, and you have to like rotate it around to look at it. It's hard to understand what's going on. And we don't really have anything, and this only works on 2 dimensions anyway. So the question is really what do we do? And the idea with the slicing is if we only had one factor, you guys all know this from high school, right? Does anyone not remember function plots in high school? This is your review. So your factor is here. So as this varies, you can basically see the variance in the home price. So if this is like the crime rate, if the crime rate is really low, your home price goes up for some reason. That's probably true. If your crime rate is really high, your home price also goes up. Maybe because there's lots of stolen goods in your house, or the pirates buried treasure under it or something. But this is something I think is relatively easy to understand. It communicates the fact that there's this continuous model going on underneath the thing. You can actually get a sense for sort of where is the minimum value and sort of what is the rate of change and what kind of function are you looking at, like if it's a logarithmic or quadratic or any sort of thing like that. And the idea that we worked on, which actually turned into a paper, was this idea of like extending this to any number of dimensions. And the idea is if you take a 2-dimensional function, just as an example, so this blue thing is illustrating a 2-dimensional function. So the light areas are higher values of the function, and the darker areas are lower value. And what you can do is you can pick something called a focus point, which is this, and then you can take a slice in each direction, right? And then you just put a function plot across the thing. And so you're looking at a cross-section for everything. And of course, this can extend to any number of dimensions. You just have more and more and more cross-sections for every single type of function. The problem here, though, is that you have to pick this focus point. And if you pick a bad one, you won't see anything. If it's flat, like if over here, the function is basically flat, like nothing is going on. If you put the focus point there, you won't see anything. It'll just be a flat line, and you'll be like, oh, nothing happens. But if you put it here, you get a lot of interesting interactions. And so the idea was actually, rather than picking a single one, is you pick a whole bunch of focus points. So you sample this whole space in an efficient way. And you project all the slices down, and then you get a plot like this. So this is every single horizontal direction, basically all the cross-sections in the horizontal way, and this is all of them in the vertical way. This particular function is symmetric, that's why they look exactly the same. But if the function isn't the same in both directions, then you'll actually see different things in these kinds of plots. And what's nice is if you go back to the 13-dimensional example with the home prices, is you can actually get something like this, where you get a plot for every single factor, and you get a sense for sort of what's going on with the home prices according to each of the individual factors. So on the x-axis, you basically show the different values for the factors. So this is like the age of the house. So the age of the house increases from 0 to 100 years. The y-axis, it's all synchronized, so you can actually read across these plots. So this is always on the same scale, the y-axis. But this is the home price for all the different plots. And then, each one of these lines, this is one particular slice. And the idea is by looking at these different slices, you can get a sense for which sort of models, how are the predictions working in these different, according to these different factors. And you can use this to answer the questions that I had before, the 4 questions. So the one is like, the most expensive house. So this, again, is actually pretty easy for this. So, here you can just sort of find where the line is the highest across all these plots, and that's the maximum price of the house. So here it's 35 money units. I don't remember how this scales. You can sort of get more interesting things. So here you can say, like, okay, so which factors impact the price of the house more? And here what you want to look for are where are these lines really moving? So where are they not really flat? And so you can sort of see that the crime rate, that sort of affects the price of the house up to a point. So after a point, it basically doesn't affect the price of the house anymore. So if your crime rate is 90%, it doesn't affect the price of your house versus if it's 70%. But if your crime rate around your house is 90%, you should probably leave. Or build like a castle. Or the number of rooms. This one I find really interesting because this kind of, it starts to go down as the number of rooms increases, and then it goes up by a lot. So that's kind of neat. This is the percentage lower income status of the population, which they record for the house price stuff. So this one doesn't have so much of an effect as the other ones. Yeah?
and understand the question. So these are slices on the fitted data? Or
Yeah.
On
So the data set like I have is just samples of house prices with, and then you just run a regression model on it and look at it. So the other one, actually, so this one I like a lot. So the question is safety. So there's like sort of, you can look at safety as like public safety, like crime rate, or you can look at it as like environmental stuff. And like the crime rate affects the house price, but no one cares about the nitrous oxide concentration around the house. So that doesn't affect your house price. So that's interesting, I find. But yeah, this is all based on this model, what this model has learned. So this is actually, this can be a problem. But this also actually gives you a lot of insights. So like, I mean, I actually I forgot to include it in here, but I built different types of regression models. And depending on which one you built, there was one that it predicted that the home price would increase like quadratically as the house price went up. And that was not good. So we didn't use that regression model. But that was sort of like if you ran the sort of numerical tests for the regression model, like in terms of comparing, like testing data to predictions, it was very accurate. But if you looked at sort of the shape of the curves that it was giving you, it was making these nonsensical predictions. So I think the reason was there was no like crime data out here, because the crime rate of 80% is really bad. But this you can actually get a sense for these kinds of curves from these curves that you can't normally get. And yeah, so here you can actually get a sense for the relationship. Like here it's kind of flat. You could say linear or non-existent. Here you have sort of like a cubic function sort of relationship where it goes down and then kind of curves back up. Yeah, and so it turns out that like there's lots of different applications for looking at these slices that people want to use. So some other ones, other than just looking at regression problems, people have computer simulations where there's a whole bunch of actually. Where do you go? You had like where you had all these different factors for fitting the molecules in a space. So it's just like computer simulation, and you're looking at like how does this affect my frame rate, or in this case it's how do these parameters affect the hurricane hitting the south part of North America. It's important to understand the effect of these parameters. So there's also like numerical optimization algorithms where you want to understand how do you tune your optimization algorithm to find the minimum. So here again, visual inspection can help you get a sense for what does the function actually look like and how wavy it is, and will my optimization algorithm get stuck. And then the general kind of cool stuff is looking at, this is a Klein bottle, those bottles that like stick into each other. This is like in 3D it intersects, in 4D it actually doesn't. It's like a Mobius strip actually. So the Mobius strip in 1D will intersect itself because you twist the paper and then if you put it down it folds, right? Tears. But in 2D it's fine. In 2D it's flat. In 3D it won't intersect. The Klein bottle is like the 3D version of that. So in 4D it doesn't intersect with itself, which is weird. So things get weird in 4D and then they get even weirder in the higher and higher dimensions. Like we don't have good ways of looking at this. So this is generally what I've been trying to do. So these are other application areas that we sort of explored by using these sort of slices. Another thing that we actually looked into is like, what sort of stuff do people want to use these things for? So if we go to like a user, like a target user, and say like, what are you looking at in your data and what are you trying to understand? We developed sort of a task taxonomy, like a set of tasks that people want to do with continuous data. And the interesting thing, at least in the visualization research world, is people have actually come up with lots of task taxonomies, but they're all designed around like discrete data visualization. And so what we did is rather than kind of like sometimes you could either start from scratch and then basically ask a whole bunch of people like what kind of tasks you want to do and build it all up. What we did instead is we started with a discrete set of tasks and we sort of tried to figure out, how would these discrete analysis tasks extend to, when you have this sort of input-output relationship that we want to look at. It turns out in here, like one thing that people often want to do with their data is sort it, which doesn't really make much sense when you're looking at sort of like this sort of input-output relationship. So this was gone. but 9 of the 10 other ones. And then we made this cool table, which is probably easier to read online or in the actual paper. But one example that I actually want to call out is, where is it? Characterized distribution. So the idea here is, you want to sort of understand what sort of shapes does the function that you're fitting look at, have. And one example where this is really useful is actually looking at performance, like if you're trying to figure out the performance of your machine learning algorithm as you vary different meta parameters. So this is not the data, this is all the other stuff that controls your machine learning algorithm. Usually you have these competing measures of precision and recall, so like the accuracy of your model. And you want to look at it with respect to a whole bunch of different parameters. There's a whole bunch of different meta parameters, and depending on how you set them, you get good or bad performance. So here you can see like this P2 thing. If you set it to this like 0.15, you'll actually get really bad performance on your machine learning algorithm, whereas like you really need to set it specifically here. And it really matters how you set this P2 parameter. Whereas this P1 parameter doesn't really have any effect on the precision. By reading these, you can kind of get a sense for, how should I set these parameters. So here you want to set this third parameter pretty low, so you get good performance in terms of recall, but you need to be careful that you don't pick it up with the precision. And so by looking at these sort of shapes, you can get a sense for, how do I set these parameters, these meta parameters for my machine learning algorithm, as opposed to just sort of setting them randomly, or doing like a grid search or something like that, which can be really slow. One thing that we also did, so we looked at there's a whole bunch of competing techniques for looking at multidimensional data. So this is all of them across the top. So there's hyperslice, which is those black and white plots I showed you before. Then there's some ones based on geometry, which reading the papers they're very dense and very hard to read and very hard to understand what they're doing. Or this sort of 1D slice effect. And what we did is we sort of measured, so this is we asked visualization experts, and this one we asked regular users, which one do you prefer? And the darker the purple, the better it is. In terms of how well each of these techniques performs these different tasks. And the sort of takeaway is some of these more complex geometry things, they're better at extracting particular features. Sort of the 1D slices is a generally good first try if you don't know specifically what people are looking for. And then the last thing I want to talk about is sort of another project that we worked on. You notice here the 1D slices don't work well, and basically nothing really works well for these 1D and 2D relationships. The only thing that works well is this hyperslice technique. And this turns out to be really important when we want to look at things like polytopes here, or so this is a Pareto front, or efficient frontier if you're from economics. So this is basically if you're trying to do optimize two variables at once. You basically want to pick F1 so it's lowest and F2 so it's lowest, and you have a whole bunch of choices and they all fall along this thing. All things back here, these are worse than anything on this frontier. So you would never pick these. So you only want to pick. But the question is what does this thing actually look like? This is with two objectives. Usually you have way more than two objectives, and you can't look at them. But it turns out that if you have more than two objectives, you actually get a polytope. So something that looks like this. And you can use these sort of slices to look at these multi-objective kind of things. And the problem is taking a 2D slice. So basically you want to get something like this when you're looking at the things. Taking a 2D slice of a multidimensional object is very hard. So we actually came up with an algorithm that works. So normally what you want, so here's your polygon. So this is a 3D one. You basically take every single, and you want to produce this on the right. Okay? So this is your 2D. Taking the point where you want to take the slice in the triangle, converting it to sort of a relaxed point. So now you actually have a plane going through this point. And one thing that you criteria here is what you want to find is where this thing intersects the edges of the triangle. One cool property is that triangles have a thing called simplices, which is a triangle in any number of dimensions. They have this cool property where the edges are all, they have a barycentric coordinates, which basically describe where in the triangle you are. And barycentric coordinates have this cool property where on the edges of the triangle there's 0. And it turns out that you can use this to basically you convert this point to its barycentric coordinates within the triangle, and then you try to see if it ever touches the edges. So that's actually what this is describing. This is a over or under. I always get over and under determined mixed up, but it probably doesn't matter. So this is not a simple linear system, but you can solve this. And it turns out if the point is actually inside the triangle, and therefore the plane intersects the triangle, there will be a solution to this equation. So you have to find an x in here such that this thing equals 0, and then all of these are less than 1. It has to do with barycentric coordinates. That's why. And sometimes you won't have a solution, and the code will detect that, and then that just means that this plane is outside the thing. So you basically just run this for every single triangle, and you run around, and then here you have this triangle, you draw that line, and then you keep going, and then eventually you'll have your whole thing. And so then you can use this algorithm to sort of look at all kinds of different shapes. So here, for instance, like you can look at this 8-dimensional figure or 8-sided figure in 3D. You can see that it still has the sort of same symmetries as you move up in dimension. You also have so we can also use it to look at these multidimensional Pareto fronts, which no one's really been able to do before. This is going to get extended into another research project, but the idea here is you can actually see the trade-off between. So you sort of get some of the benefits of the Pareto front, where you can see the trade-off. So everything along this line assumes that you hold all the other measures constant, and then if because of the way Pareto fronts work, if you want to move from this line to this line, you have to decrease some of the other parameters. So you have to lose something in the other objectives to move from here to here. But you can actually see how much moving from here to here will buy you when you actually decrease those other parameters. And so that's kind of nice. So in conclusion, so a lot of my research that I'm working on now is actually trying to come up with a way of evaluating, with users, how effective these kind of things are about teaching them about their data. This is quite hard. We don't really have techniques for doing this that I know of. The other stuff I want to work on is, I'm working right now on basically putting all this into an R library, so you can just throw in data or throw in a function, and it will give you slices, and it'll give you an interactive viewer. I'm also working with some researchers doing stuff on multi-objective optimization to try and build a multi-objective optimization system for them. So with that, I have a website and an email address, which this will go away in July. And I have a GitHub thing too, where I put all my code, and all that. And with that, I want to thank you for listening. And if anyone has any questions. Yeah.
Do I get to write your kind of, you do this at the university in order to have other research areas to see what they otherwise cannot see?
Yeah.
And what research areas? You mentioned economics.
Yeah, so we work with some economics people, we work with some physicists. We work with some geometry people, like people studying there are math people who study polytopes. There are, who else do we work with? People studying, so this is an algorithm trying to segment brain structures from MRI images and the performance of the algorithm. It's like a bunch of different diverse kind of fields.
Thank you.